Alrighty. Am I on, guys? All right, well, welcome back, guys. When I go to the Zoom login page, it has a list of all the upcoming meetings, which of course I've preloaded it with every class meeting for every one of my classes for the rest of the semester. And so it looked like an infinitely long list, but now it's just got like 3 or 4 things on it. So I guess we must be reaching the end. All right, so I have, I guess, 3 things that I want to make sure we do today. This is your last chance to ask me for questions for help with the current homework set. Some of the questions on the homework set have to do with Gauss's divergence theorem, which we have not discussed in detail, so I want to show that today. And then whatever time we have left, we can just kind of review the entire semester in one day to prepare you for the final exam. So let's repeat the schedule we talked about last time. On today is regular class meetings, office hours this afternoon. Monday I'll have office hours from 11 to 1. And then your exam will be Wednesday morning. It'll be available around 9 and last until Saturday night, 10 p.m. Malik, you have a question?
Yeah, so I just had a question on the homework.
Okay.
Okay.
You're changing my volume here. Okay, go ahead. Yeah, what's the question on the homework?
So for number 12, it doesn't like tell us to use any specific like method to solve the integral. And I'm pretty sure you're supposed to use, or like they want you to use divergence theorem. But I tried using Stokes' theorem initially, and I don't know why I wasn't able to get an answer, and I was wondering if like maybe you could help me with that. I'm probably just missing something, but.
Okay, so a few comments there. First of all, they said compute this integral. You can use any technique you want, and I've tried to equip you guys during the semester with as many tools as I can so that you can compute, so that you can solve any problem. And in particular, when it comes to computing integrals, you always have the very definition of what an integral is if you want to go ahead and do the computation. So this one, if I recall, let me pull up the problem here. You're computing a surface integral, right, around the boundary of a cylinder. Yeah, is that what you have, Malik, as well? Yours is a solid cylinder.
It's a double integral. Mine's is, I don't know if that makes it.
Yeah, so just a comment about that. People's notations over the years have varied a lot for integration. You always see the integral sign as one clue that you're doing an integration problem. There always has to be some indication. Well, so there's an integral sign. Sometimes people write it doubled or tripled to emphasize the fact that they're doing a 2-dimensional integral or a 3-dimensional integral. And by that I mean when it comes to the chopping up of a set, and you're going to be measuring the sizes of the pieces, some people want to use a double integral sign when they're talking about area and a triple integral sign when they're talking about volume. I haven't done that. I just want to consistently use a single integral sign. You're welcome to do it whichever way you want. The same thing, by the way, when you're doing a line integral over a closed loop, some people like to put a little circle around the integral sign. It's fine, I won't. And in the same way, in a problem like this, where people are doing a surface integral over a closed surface, so this is a surface with no boundary of its own, they like to put a similar circle, well, more of an ellipse, that kind of hugs the integral signs. So that's the variation that you see in the integral sign. Somewhere around it, you have to put an indication of the set over which you're doing the integration. And somewhere next to it, you have to put an indication of the scalar valued function that you're integrating. This one shows a vector field, not a scalar, but that's because it has the little dot in there next to the D with a boldface S. And you guys know what that means. It means that you're actually computing the integral of the scalar valued function, which is that vector field dotted with the unit normal. And they have to, they didn't actually say, but they intended, I guess, for you to use the outward normal. It's interesting they didn't say that. That's the kind of the tradition in these examples. So when it comes to computing this, you could just literally go through that. You have to compute a surface integral over the boundary of the cylinder. Along the way, you will have to write down a formula for the outward pointing normal, unit normal, so that you can compute a dot product. And that's not impossible in this case. You would need to break the integral into two parts, well, three parts, I guess. There's the top and the bottom, which are flat, so the unit normal is easy to pick out. It either points straight up or straight down. That would be 0, 0, 1 or 0, 0, negative 1. And then the normal on the side, you have to separate the integral around the cylindrical side, and that's the normal there would be the one that points at the point x, y, z. The normal would be the vector x, y, 0. So that would point level to the xy plane, but it would be pointing away from the vertical axis. And that would be a normal vector. You could scale it by its length to get a unit normal. So you have that method for computing the integral if you want. You also have the thing where I talked about parameterizing. You could parameterize both the top and then the bottom and then the side surface. And then the whole business of getting unit normals is obviated. You just have to take the dot product with the TU cross TV thing. So that's a second way to compute this one. Now a third way is Malik wanted to try to use Stokes' theorem, which is a good idea because Stokes' theorem says that you can recompute a surface integral as an integral in a different dimension. The surface integral is two-dimensional, and Stokes' theorem would relate that to a one-dimensional integral. And Stokes' theorem is nice because you can apply it to any surface, but you can't apply it to any vector field, not just any vector field. You can only apply it to vector fields which are the curl of something else. And that's kind of an annoyance. And in fact, not every vector field is the curl of something else. The way that you can test that is by taking the divergence of the thing you're trying to integrate, the vector field you're trying to integrate. And if you don't get the zero vector field, the scalar field, then the vector field you were given was not the curl of anything. And there's just no way to use Stokes' theorem in that case. And that's what applies here. You simply cannot use Stokes' theorem in this case. But you have one more recourse, which is Gauss's divergence theorem. That also relates surface integrals to integrals of a different dimension. But in Gauss's theorem, the dimensions are not 0 and 1 or 1 and 2. Now they're 2 and 3. Gauss's theorem will relate a surface integral to a volume integral, an integral over a solid three-dimensional set. And well, that's what actually they wanted you to use in this case. There is a kind of a drawback. Like all these other theorems, Gauss's divergence theorem will say that an integral in one dimension will match an integral in a different dimension. On the one side, you can have any set you like, and on the other side, you can have any vector field you like. But then the set that you're integrating over on this side has to be the boundary of something. So you can't use Gauss's divergence theorem on just any old surface. You can only use it on surfaces which are the boundary of something. And likewise, the function that you're integrating on the other side, I'll write it down in a second, that has to be the divergence, a kind of derivative of the thing you had on this side. So you can't use Gauss's theorem for arbitrary three-dimensional integrals either. So none of these theorems that I'm giving you, I mean, all of the theorems that I'm giving you relate an integral of one dimension to an integral of the next dimension. But in every single case, you're not guaranteed that you'll be able to use that theorem in a case where the dimensions are right. You have to either have a special kind of a region to integrate over, because it has to be the boundary of something in the larger dimension, or you have some restrictions of the kind of functions that you can be integrating, because they have to be the derivative of something on the other side. So that's a long way of saying that you guessed right, Malik. It is not a question of using Stokes' theorem, it's a question of using Gauss's divergence theorem. So let me not go further with problem number 12 just yet, because I want to, if there's other questions on the homework that really do use Stokes' theorem or something else other than Gauss's theorem, let's do those first, and then I'll show you how the divergence theorem works. So, does anybody have a question about another one of the homework problems? All right. In that case, let's turn to this last theorem. Let's just get it out of the way so we understand it. Right. I got these slides. I actually had them ready last time.
Dr. Reason?
Yeah. Well, hang on.
Okay.
Here, because I just pulled out my piece on that computer. There we go. All right. Yes, what was your question, Enrique?
My question was more in regards to Green's theorem, if we can discuss it.
Yes, what do you want to know about Green's theorem?
So I just had a question in regards to a specific problem I had on the homework.
Okay, which one?
Question number 5, it was the arc of the cycloid shown, parameterized by a given function over the interval 0 to 2 pi.
Yep. So what did you do?
So, God, great. Now I am.
Well, here's what you were supposed to do. So they show you this arc,
Yes.
and they say, what's this area? And they've even parameterized the curve for you. So that's a hint that you're probably going to use Green's theorem, because otherwise, why would you care about the curve at the boundary of this region? Okay, and so you take t's in the interval from 0 to 2 pi. So I would need this parameterization if I were going to integrate along the curve, but I don't want to integrate along the curve. I want to calculate an area. So area, can I call that set C for cycloid? What does an area have to do with any integration at all? Enrique, why don't you tell me, what does this have to do with integration?
Well, whenever you're integrating, you're taking the area underneath the curve itself.
No, don't say it that way. I mean, yes, when you integrate a function of one variable between something and something, you guys know that you can interpret that as being the area of the region that lies under the curve and over the horizontal axis. So that would be perfect for this. But in order to use that understanding of area, you would have to be writing y as a function of x along this curve. And then whatever function you've got, that would be the function that you integrate from whatever this x coordinate is to whatever that x coordinate is. But I wasn't given y as a function of x, and you would have a hard time getting y as a function of x. This curve has been given to you implicitly. If you want to think of this as the graph of a function explicitly, well, you know, we did that kind of thing early in the semester. You're here with a parametric form. You want to end up here with an explicit form. And the way I've usually encouraged you to do that is go by way of the other corner. First, get the curve written implicitly. So you need to take x equals this, y equals that, and then you would have to eliminate the t's and figure out the relationship between x and y. Well, you can try, but you're going to have a real hard time getting all the t's out of this. It's very difficult to figure out an expression that has just x's and y's in it. Here's what you've been given is 2 equations in the 3 letters, x, y, and t. And you want to replace that with just 1 equation in the 2 letters, x and y, to get the t's out of there. But it's hard to get the t's out. And even if you did, you would only be at this corner. Then you would have to take that equation with x's and y's in it and solve for y as a function of x so that you could end up in this corner. And then you could use your idea of integrating, just integrate whatever function you were using in this corner. So that's a long way of saying you need a different interpretation of area in terms of integrals. You got any others? Anybody else remember an interpretation of some way of connecting areas with integrals?
You can integrate along the curve, which gives you the area.
Yes, you're using Green's theorem when you say that. There's an intermediate step that I want you guys to feel comfortable with, which is you get the area of any solid set by integrating 1 over that set. I mean, this is kind of important to me that you guys feel like this is a natural thing to do. If you've understood what I've said a million times about integrals, this will feel natural. The way to compute this integral is you take this set C, you chop it up into little bits, you multiply the area of each little bit times, well, the value of the function is always just 1, so you're just going to take the area of each little piece and add those together. And then, of course, you will get the area of the entire thing. So an area can always be written as this stupid-looking integral. And likewise, every volume in three-dimensional space, you can get the volume of any set by integrating the constant function 1 over that solid set. This would say dv instead of dA. And likewise, the length of any curve is the integral of 1 over that curve. So please make sure that you understand the very feel of what integrals are so that this kind of an equation feels natural to you. If you can get to that point, then you can start to use how you just said about integrating around the boundary, because at this point, Green's theorem will come to your aid. So this right here is by the very definition of what an integral means. But the next equal sign will come from Green's theorem. Green's theorem will say that an integral of a function of 2 variables over a 2-dimensional set will be the same as an integral over the boundary of that set. You need to be computing a line integral of a p dx plus q dy, where you can actually choose any p and q that you like, as long as the partial of q with respect to x minus the partial of p with respect to y comes out to be 1. And the book likes to use this combination, put a 1/2 x in there and a minus 1/2 y in there. And then the partial of this with respect to x will be 1/2 minus the partial of this with respect to y, which is negative 1/2. That'll add up to 1. So now you've reduced the problem to computing a line integral. And the part that a lot of students forget on this line integral is that this boundary of C means you need the entire boundary of this closed set C, this bounded set C, with the boundary taken counterclockwise. You're supposed to be walking counterclockwise along the boundary of the set C, which means 2 things. There is this horizontal line segment that's part of the boundary, and it needs to be part of your calculations. And the other part of the boundary needs to be traversed right to left instead of left to right. So I would write this as an integral over the first curve, and I'll keep this minus 1/2 y dx plus 1/2 x dy. So that's this curve C1, and then I'm supposed to take the top edge traversed counterclockwise still, which most of you would call backwards. So I'll write it as minus the integral over the curve C2, where C2 is this top arc traversed from left to right. And of course, I'm integrating the same thing, minus partial y, as integral of y with respect to x plus 1/2 x dy. It's at this point that you can start to use this parameterization, because now you've got a line integral. You got 2 line integrals actually, and in each case, you need to parameterize the curve that shows up down here under the integral sign. And once you have a parameterization, you guys know what to do. You substitute away all the x's and y's that show up in your integrands, and you take the dot product with your velocity vector. So I guess all I would do now is to say, is to just literally parameterize here. For the curve C1, you're only choosing points that have a y-coordinate of 0, so my position at time t might be t comma 0, and I'll use t's that go from 0 to, where do I end up here? When t is 2 pi, my x-coordinate is 2 pi, my y-coordinate is 0. Yeah. So if that's my parameterization, then your velocity, that's the phi of t, then the velocity vector is 1 comma 0. It points straight to the right. It's a unit vector already. And the vector field that you're computing, P comma Q, when you compose that with phi, that's supposed to be this, minus 1/2 y dx. Sorry, just the P and Q. Minus 1/2 0 times 0, and then plus 1/2 times t. And then what you do to compute the line integral over C1 is you integrate over this interval of t's, and then you rewrite the original integrand. That's obviously a 0 there, and 1/2 t here. And you dot it with your velocity vector, and integrate that with respect to t. And I think you guys can see that this inner product is already a 0, so the integral of it will be a 0 as well. So you guys are off the hook on this problem if you forgot to include the bottom edge. But don't forget it in general. In general, you need to remember that even if there's a bottom edge, somehow, or side edge that you didn't think was relevant, it is relevant. It has to be part of Green's theorem. You have to integrate around the entire boundary. And then the other curve, I put in a minus sign here already so that you can traverse this one from left to right the way this parameterization would go. So in this case, that's my parameterization phi. The velocity vector is more complicated than this one was. I'll get 1 minus cosine of t, comma, positive sine of t. And so the integral over the curve C2 of p dx plus q dy turns out to be the integral from 0 to 2 pi of this first part of the velocity vector times, what was it here? Minus 1/2 times y. So that's minus 1/2 times, here's the y coordinate. Oh, I understand that. And then you have to add in 1/2 times x, which is t minus sine of t, multiplied by this x, the other component of the velocity vector, and integrate that with respect to t. So there's a Calc 1 integral for you to do. I guess I will leave it to you to actually finish the computation. How's that? So, Enrique, you were the one that asked that. Does that answer your question?
Yes. What I was failing to do was recognizing that since it has to go in a counterclockwise manner to do the minus of the integral versus the addition of the integral. That was the only error I had in my calculation.
Okay, well, that's the only error that you had, but I know because I've spoken to several other students that there were a few other errors, which is failure to include the bottom edge, and failure to recognize that this is Green's theorem in the first place, which would have told you that you need to have a counterclockwise closed loop. Good. Any other questions on the homework that I should clarify for you? All right, let's turn to Green's theorem. Excuse me, Gauss's theorem. You can't really just say Gauss's theorem. Gauss was such a he was not only a famous mathematician, a famous physicist as well. So he's got a lot of theorems named after him, but this is the one called the divergence theorem, and it has to do with relating integrals. Again, it's integrals in two different dimensions, but the setting now is, well, like we had in Stokes's theorem. You start off with an arbitrary vector field in three-dimensional space, and an arbitrary subset, in this case, a three-dimensional object. In Stokes's theorem, we had an arbitrary surface floating in three-dimensional space. Now we have a solid in three-dimensional space. And you can see I was struggling to find a letter that we hadn't already used in any other theorem. So I'm just going to call it M. Then here's Gauss's theorem in action. Like all the other theorems, it says that two integrals are equal. This one is a surface integral, a two-dimensional integral. You will be doing an integral over a two-dimensional set, namely the surface of the three-dimensional set M. And the other side is now a three-dimensional integral. That's the whole three-dimensional object in here. This will be a function of three variables, and you'll be integrating like you do with Fubini's theorem or the change of variable theorem or something. So all three variables show up, all three variables have limits of integration. You'll see it in books with this one written with 3 integral signs, and this will have just 2 integral signs because it's a surface integral. Like I said earlier, sometimes people put a little loopy thing over there. But that's what the divergence theorem says. And so I want to treat this kind of like I did for Stokes' theorem and Green's theorem too, for that matter, and the fundamental theorem of calculus for that matter. I want to go through some special cases, and then maybe we'll do an example if we have time. So, well, I had some special cases for Stokes' theorem. Let's see if I can give parallel special cases for Gauss's theorem. The first one I mentioned for Stokes' theorem said how Stokes' was a generalization of Green's theorem, and I don't really have a corresponding thing to say. But here I do have something to say in the case where your vector field on the left side is special. If the one on the left side happens to be, let's see, in Stokes' theorem I said if it happens to be the gradient of something else, then blah, blah, blah. Now I'm going to say if the vector field on the left side happens to be the curl of something else, then blah, blah, blah. And the blah, blah in this case is that if you knew that the vector field F was the curl of a different vector field G, then on the right-hand side of Gauss's theorem, where it talks about the divergence of F, now you're talking about the divergence of the curl of a G. And this is another one of those cases where these mnemonic notations for divergence and curl are handy because it reminds you of what you did with vectors. If you take a vector and compute the cross product with anything else, you'll get another vector that's perpendicular to both of these two things. And in particular, if you take the dot product with either of the vectors that showed up in there, you'll get 0. So that's not literally what's happening, but it is a true statement. So this is a good way to remember it. The divergence of the curl of G would automatically be 0. And so on the right-hand side, you'll have the divergence of, well, that's curl of G. So that'll be a 0 as your integrand, and therefore the entire integral on the right-hand side is a 0. So, oops, I forgot to finish my sentence. So that means that the integral that you have on the left-hand side will automatically be 0. And like I said, don't read too much into this. You're telling me that all these surface integrals will be 0, but there are 2 conditions. One is that your vector field has to be special. It has to be the curl of something else. And the other is that your surface has to be special. It has to be a closed surface. It has to be the boundary of something else. That's the same as saying that the surface S doesn't have any boundary of its own. Now I can weaken this part of the theorem, of this special case. I can make things a little less special. If you keep the premise that your vector field is special, if your vector field here happens to be the curl of something else, then you can use the divergence theorem over any surface, even if it isn't the boundary of something else. Like here I've shown a hemisphere. It's supposed to make you think about a hemisphere. A hemisphere is not the boundary of something. The hemisphere, you might think it's the boundary of half of a ball, the top half of a ball, but the boundary of the top half of a ball is this hemisphere skin, and also a skin that goes across the cut that you make across the equator. So that surface right there is not a boundary. I don't have this condition. And so I can't, even if I know that the vector field is special, I can't conclude that these integrals will be 0. But what I can conclude is that this integral over this surface will be the same as an integral over any other surface that has the same boundary. Okay, it's the same curve as the boundary of these 2 surfaces. As long as you have the same boundary twice, then it doesn't matter which surface you used. So this is exactly analogous to what we had with Stokes' theorem. Stokes' theorem said that if your vector field was special, in that case it had to be the gradient of some function, then it didn't matter which curve you used to integrate over as long as you had the same boundary of the curve. The boundary meant the ending point and the beginning point. So it's the same reasoning here. The reason why this is a consequence of this one is that if I have two surfaces with the same boundary curve, and I look at these two surface integrals, then if I subtract this surface integral minus this surface integral, that will give me the difference between those two surface integrals, which together would make the integral over a surface that has no boundary at all. It would be the boundary of now the entire ball, or whatever fits in, whatever shape that is that fits inside those two surfaces. And so from the top line, that would be a 0. Now you do have to be careful in this. The whole game of how you compute these surfaces relies on the fact that in the case of a solid surface, solid three-dimensional chunk, you compute these integrals with things like Fubini's theorem or something, but there's no question of an orientation. There is a question of an orientation on the left-hand side, and this has to be oriented with its outward normal vectors. So there's this three-dimensional shape called capital M. I want you to choose the normal vectors that point away from capital M. And if you do that, if you try to use that in this circumstance, if you think about the solid that's going to be on the inside of those two things when you glue them together, then this guy would use those outward pointing normals, and this guy would use these outward pointing normals. And the reason that I want to emphasize that is I want you to see what happens to the curves around the boundary. They both have the same boundary as a set of points. But if you imagine the setup that we used for Stokes' theorem to get the right orientation on the boundary, in this case, you would have to stand with your feet on the surface and your head at the arrowhead. And when you stand at the surface and try to make your left hand drag along the surface, that would force you to walk in that direction along the curve. If you do the same thing here, maybe if I turn my paper, it'd be easier for you to see. You'd have to stand with your feet on the surface, your head at the arrowhead, and your left hand dragging along the surface. That's going to force you to walk this way. Oops, that's supposed to be in the back. Sorry, I made it dotted. This surface continues all the way up here like that. So you would have to be walking that way around the curve. On the dotted lines that I drew that are in the back part of the surface, that's where you would be walking in that direction. So when you compare these two pictures, look what happens is you're walking along the part of the curve that would be closest to us, closest to the camera. You'd be walking from left to right along that arc on this surface, but on the exact same surface, that curve is written right here, and it would have you going from right to left. So you see, these two surfaces would induce two different orientations on that boundary, the part of the boundary that would be glued together when you put these things together. So when you look at the sum of the two integrals over these two parts, that would be the integral over the entire surface with its outward pointing boundary, and that would include integrating along this equator curve first in one direction and then in the opposite direction, and so those two pieces would cancel. So be careful when you use this, okay? You're trying to, you're ultimately unpacking what this theorem says, and this theorem is all about having a single closed surface that's the boundary of something else, and that forces you to use the same outward normal in both cases. So if you decide to use two different surfaces, you want to make sure that they end up with the same orientation along the curve. All right, anyway, so this is analogous to one of the special cases that I talked about in Stokes' theorem. What if your vector field is special? And special means something a little bit different, but we get the same kinds of conclusions that we had with Stokes' theorem. Now, the next thing that I did with Stokes' theorem is to say, yes, well, what if your vector field is not quite so special? Can you play the same game? And the answer is, well, sort of, but you have to put in a correction term. Because what I did here was I used Gauss's divergence theorem. I wrote out the left-hand side knowing that the right-hand side was a 0. And then the left-hand side was the part that got split into these two separate surface integrals. Well, even if the right-hand side of Gauss's theorem is not 0, you can still play that trick. If you have two surfaces that have the same boundary, you can compute your surface integral over one or the other, and you'll get the same value if you add in a correction term. And this correction term is exactly what it says you're supposed to be computing on the right-hand side of Gauss's theorem. So this now looks kind of complicated, and I can see that it is, but this is giving you a hint as a common way that you can use the divergence theorem, even if you don't have a special vector field, even if you don't have a special surface. Basically, any vector field, any surface over here, a different way that you can compute it besides the one that's given in the statement of the problem is you can replace that surface by any other surface that has the same boundary, as long as you put in a correction term that has to do with the solid space that's between those two surfaces. Okay, nobody's asking me any questions, that's okay. When I did Stokes' theorem, I had one more special case for what happens if your surface doesn't even have a boundary. So then that would be the case of something like a sphere. There's no boundary on it. I don't have a corresponding thing to tell you about when you take a solid three-dimensional thing in three-dimensional space, it can't have an empty boundary. So I don't have a fourth special case for you. I will say for you mathematician types out there, you can use Gauss's theorem or something cognate to it for three-dimensional objects that are embedded in a 4 or 5 or higher dimensional space. And then it's possible to do the embedding so that your three-dimensional thing has no boundary. And then according to the corresponding Gauss's theorem, that will mean that this integral on the right-hand side would be 0 automatically.
Could you elaborate on that?
Yes, but I don't want to lose the sort of physically minded people who actually live in a three-dimensional space. But if you take, for example, suppose that I take the set of all points x, y, z, w in R4 that satisfy the equation x squared plus y squared plus z squared plus w squared equals 1. That is a three-dimensional object because I see 4 variables, but only one equation that links them. So this is a three-dimensional object now. And if I give a name to it, the name that everybody uses is that this would be called the three-sphere, the three-dimensional sphere. Not to be confused with the surface that you see on a globe. That is called a two-sphere, the two-dimensional sphere embedded in three-dimensional space. This is a three-dimensional object embedded in four-dimensional space. Because basically, if you stand at any point in this set, you can vary any 3 of these coordinates a little bit. You just have to calculate the 4th one to match. But you have 3 degrees of freedom in which way you're going to move. So it's a three-dimensional object, and yet the boundary of this is empty. And so if you have a suitable vector field to integrate over this object in 4-dimensional space, then you're automatically going to get a 0. And when I say a suitable one, you still have to have something like this being true. It's not called curl anymore, but it's, well, I'll give you the general form of Stokes' theorem when we're done with Gauss's theorem. So yeah, that's often la-la land for those of you who only think about the 3 spatial dimensions that you know about. Don't worry about this kind of thing. And by the way, don't try to use time as your 4th dimension, because the special relativity people tell us that in 4 dimensions I should be putting a minus sign there instead of a plus sign. So That's a different kind of four-dimensional space. Okay, but I do want to point out a kind of a cute example. What if I give you a surface that actually is the boundary of a three-dimensional object? So like the one you had in the homework problem, take the boundary of the solid cylinder. So that's the label and plus the tops and the bottoms on a tin can. And what if I give you a vector field that happens to be the curl of another vector field? And then I say, please compute this surface integral. So this would be kind of like the problem that was given to you in the homework, the one that you already asked about, except our vector field was not the curl of something else. But if it was, you would have two different ways to go to figure out the value of the surface integral. Well, multiple ways to go, besides literally computing the surface integral by parameterizing your surface. The other thing you could do is to say, hey, my vector field is special, and so I can use Gauss's theorem, Stokes's theorem, to say, look, this surface integral can be written as it's the surface integral of the curl of some other vector field dotted with ds. And by Stokes's theorem, when you see a special, this kind of special vector field on what I call the right-hand side of Stokes's theorem, then Stokes's theorem lets you rewrite this as a line integral. You replace the surface in question by the boundary of that surface, and then this vector field returns to being just the thing you computed the curl of on this right-hand side. All right, so then you start thinking about, okay, I got to parameterize the boundary of this surface. But if you choose a surface that is the boundary of a three-dimensional solid, and I will use, for example, that tin can, or what if capital M is a three-dimensional ball, so that S becomes this sphere on the outside of the ball? Well, then the boundary of that set will be empty. I've said this before, there is no boundary to a sphere. There's also no boundary to the tin can. I mean, there's a couple of kind of rough edges where if you want to continue walking, you'll have to kind of tip over from the label of the can to the top surface, but you can keep walking in any direction that you like at any point on the outside of the can. So there's actually no boundary. The boundary of such a surface would be the boundary of a higher dimensional object. And that's a feature of this boundary operator, is that when you take the boundary of something, you get the empty set. It's completely analogous to what happens if I give you a region in, let's say, two-dimensional space. If that's my M, I can look at the boundary of it, that would be a curve, but now this curve is a closed curve, so it doesn't have endpoints. The boundary of that closed curve is the empty set. So this is sort of a one dimension up example of the same thing that you see here. So in this case, you're computing a line integral, but it's a line integral over an empty curve. So there's nothing to parameterize, and so this whole integral is going to be a zero. So that's what you get from looking at this integral and thinking to use Stokes's theorem. Today, I'm telling you, yes, that's a surface integral, but you can use Gauss's theorem to compare it not to the next dimension down, but to the next dimension up. So here's how you would evaluate the same integral using Gauss's theorem. You say to yourself, well, my surface is already the boundary of a three-dimensional solid. So I'll just I'll write it that way. It's the boundary of a three-dimensional set, and you've got some vector field to integrate. Gauss's theorem can then step in to say, aha, if you have to integrate over the boundary of a three-dimensional solid, that can be rewritten as an integral the next dimension up. So this is now the integral over a three-dimensional set. And when you do that, you sort of take the derivative of the vector field here, and this derivative in this case means divergence. So I rewrite my integrand. I take the derivative in this sense. You make the region of integration go up a dimension, and you take a derivative to come down, so to speak. Anyway, that's Gauss's theorem. And so I see now that I have to compute over a much larger set. But here's the function that I need to integrate. That's a scalar valued function. Divergence is scalar valued. But here's the thing, I assumed at the beginning that, in fact, I needed it over here. I assumed in the beginning that my vector field was special. It was the curl of something. And the consequence of that is when you take the divergence of such a vector field, this is what I had written earlier, the divergence of the curl of a vector field is just the scalar field that's always equal to 0. So your integral over here is always 0. Your integrand is 0, rather. And that makes the integral equal to 0. So this is a very special case, and what it leads to is the fact that the integral is going to be 0. This is the one kind of setting when you have your choice of either using Stokes' theorem to go down a dimension, or you use Gauss' theorem to go up in a dimension. Generally, you can only use Gauss' theorem when your surface is special, and you can only use Stokes' theorem on a surface when your vector field is special. And if you make both of them special, you can either go down a dimension by Stokes' theorem or up a dimension by Gauss' theorem. Cool, huh? All right. This is all I wanted to say about Gauss' theorem and its generality. It would probably be appropriate for us to do an example of Gauss' theorem. Would you guys like to use that one from the homework that was asked about at the beginning? Let me pull that problem up again. How much time have I got? Oh, crap. Well, you know what? Maybe I don't know.
Can I ask a question?
Yes, go ahead.
Why did you change from F to G for the Stokes theorem on the left?
Because Stokes' theorem requires that the vector field that I integrate be the curl of something else. Both Stokes' theorem and Gauss' theorem allow you to have an arbitrary vector field on one side, but on the other side, you have to have a vector field that is somehow a derivative of the thing you had on that side. And
Yeah.
when I went to use Stokes' theorem puts the surface integral on the right side of the equation. So I could only make progress by using Stokes' theorem if I was able somehow to recognize my vector field at the beginning as being the curl of something else. And that something else is what shows up on the left-hand side of Stokes' theorem. You can't put F here. What goes here has to be the vector field that you took the curl of to get the right-hand side vector field. So here I started off with a vector field called F, but I could make no progress unless I could write that F as being the curl of something else. You can't expect Stokes' theorem to help you too much with an arbitrary surface and an arbitrary vector field on that surface. Stokes' theorem would let you get away with an arbitrary vector field, but only on a curve. It lets you get away with an arbitrary surface, but only with a special vector field.
Okay.
You don't sound convinced.
I'm sure I'll figure it out.
Well, I know that this stuff is hard, guys. I get it. But I'm trying to say over and over again that we have all these theorems. In fact, maybe this would be a good way to use my last 2 minutes. We have all these theorems that say that you have integrals in a small dimension and a large dimension that are equal to each other. So it's always two integrals that will be equal, but you'll always have two dimensions involved that are off by 1. The fundamental theorem of calculus has a zero-dimensional integral equal to a one-dimensional integral. A zero-dimensional set just means a couple of points, and in our case, it was just the two endpoints of an interval. Specifically, that means that this is the boundary of this. I guess I changed that. That's a brace. And then you could be evaluating any function on this side, but this kind of zero-dimensional integral just means evaluate the function at the 2 points and add or subtract. On this side, what has to show up is the derivative of that function. That's why you spent all of your time in calculus finding antiderivatives as you were trying to go from that side to this side. When we got to Green's theorem or Stokes' theorem, then you had one-dimensional integral equal to a two-dimensional integral. So you have a curve on this side and a surface on that side, but they have to be linked in the sense that the curve has to be the boundary of the surface. Points, boundary of an interval, curve is the boundary of the surface. You could have any vector field here, but then on the right-hand side, you have to put a kind of a derivative of that vector field. And now we have Gauss's divergence theorem, and it talks about matching a two-dimensional integral to a three-dimensional integral. You can have a surface here, but it has to be the boundary of a three-dimensional set, the same three-dimensional set you have on the right-hand side. And you can put any vector field you like on the left-hand side, but then the one that shows up on the right-hand side has to be the divergence of that vector field. So they're all kind of analogs to each other. And the general statement of how this works is called Stokes' theorem. The statement is you have to have what's called a arbitrary dimensional manifold. Manifold means it's a smooth something or the other, and it has to be oriented. I talked about the Möbius strip. That goes here, its boundary goes on that side. This has to also be given the appropriate orientation. What goes on this side is what's called a differential form, and then on the right-hand side is what's called the derivative of that, or the differential of that differential form. So I don't want to do any more with this, because especially our semester got shortened this semester. I will point out that the book, actually the very last section of the book, if I remember correctly, discusses exactly this kind of a thing. It takes a whole lot of, you have to swallow a whole bunch of hard to believe stuff, but it does give a very pretty form of a theorem, which when you untangle what it means for vector fields on surfaces and three-dimensional objects, turns out that Gauss's theorem, Stokes' theorem, Green's theorem, and the fundamental theorem of calculus are all just special cases of this. And I'm trying to indicate how the notations differ in each one of these cases, but they all have that same spirit. Well, that took longer than I thought, so I didn't really have a chance to summarize anything else during the semester. I know we're over, but do you guys have any big questions you were hoping I was going to address today? No. Okay. Here's what I'm going to do. I'm going to remind you we do have office hours this afternoon if you want to check in. I'll also schedule other office hours for Monday. And then if you need anything else, send me an email and I'll try to respond to it. And then be ready for the test on Wednesday. Okay? Alrighty, guys. I'm sorry it was a hard semester, but I appreciate you sticking in with it.